In this lecture, we get to put together the picture that we've developed in the previous two lectures. So in lecture 2, we talked about what the universe looks like. You stand outside on a clear night and look outside with perfect vision. What do you see? What we found is that what you see is a set of galaxies like our own. Every galaxy has something like 100 billion stars in it. There's something like 100 billion galaxies scattered throughout the universe. The good news is that they're scattered uniformly. There's the same density of galaxies all over the place. The more interesting news is that everything is expanding. So the universe is smooth, pretty much the same everywhere, and it's expanding, it's getting bigger. The galaxies are redshifted. Their light that is coming towards us leaves the galaxies at a certain wavelength, and when we receive it, the wavelength is longer, just as if those galaxies are moving away. In the third lecture, in the previous one to this one, we discussed Einstein's theories of special relativity and general relativity, his theories of space and time. In particular, general relativity was the lesson that what we perceive as gravity is a manifestation of the curvature of space and time. Space and time are combined together in something called space-time, and that one four-dimensional space-time is dynamical. It can stretch and move, and the results of those stretching are what we perceive as gravity. So what we want to do in this lecture is take the idea of a smooth, expanding universe, a universe that is the same everywhere throughout space but growing as a function of time, and understand it in the context of general relativity. What does Einstein's equation, what does the relationship between stuff in the universe and the curvature of space-time have to say about the idea of a smooth, expanding universe? So one thing that we mentioned, that's worth emphasizing again, is that the fact that the light from distant galaxies is redshifted when it gets to us is not, strictly speaking, a Doppler shift. The Doppler shift is what happens when you have two objects with a relative velocity. One object is moving toward the other one, and when it emits something, whether it's a sound wave or a light wave, that something has its wavelength squeezed, and you observe it as a shorter wavelength thing, either a higher frequency sound or a bluer ray of light. If it's moving away from you, the wavelength would be stretched. That's the Doppler effect. A very similar thing happens according to general relativity, but it's not the Doppler effect. It's not that this thing is moving toward you or away from you. It's that the space itself is expanding in between. That is the origin of the cosmological redshift. It's that the space-time itself is dynamical. So the amount of space is getting bigger, and we're going to try to understand that in a slightly more quantitative way. So talking about quantitative ways, we'd like to ask, how big is the universe? Is that a question that makes sense? And the answer is we don't know. We don't know both how big the universe is or whether the question makes sense. What we know is that we don't see any boundary to the universe. Because in Einstein's universe, space and time are dynamical, we can imagine different shapes that space could take. In Newton's universe, it was kind of obvious that if you went out in space, it would just go on forever and ever. Space just extended in infinite directions. On the other hand, in Einstein's universe, things can be curved. If things can be curved, they can be curved in on themselves. So we could certainly imagine a finite universe, a universe that had the shape of a sphere, for example. But what we see when we look out into the universe is we do not see the back of our heads. We do not see any evidence directly that the universe that we observe is finite in size. So that doesn't mean that it's not finite in size. It's just that we don't see any wrapping around or any edge to the universe. But it's not a complete surprise. We only see a finite part of whatever universe there is. That's for two very simple reasons. The first reason is the universe has a finite age, at least since the Big Bang. For reasons that we'll talk about later, the time between now and the Big Bang is fairly well determined to be about 14 billion years. Our best guess right now is something like 13.7 billion years. But it's not a guess, it's something that the data are telling us is true. So 13.7 billion years old, but remember that light travels at a finite speed. 1 light year per year is the best way of thinking about what the speed of light is. So if light travels at a finite speed, and the universe has a finite age, light has only been able to travel a finite distance between now and the Big Bang. So even if the universe were infinite, even if it did go forever, we couldn't see all of it. We can only see a certain patch, the patch from which light can get to us in less than 14 billion years. So we don't know the size of the universe. It could be infinite or it could be finite. but we nevertheless talk about the universe expanding. So how does that make sense? If you don't know how big something is, how do you know it's expanding? What we know is the relative size of the universe. By this we really mean the relative distance between different things in the universe. So just take two galaxies, and we know that they're moving away from each other. So we can ask quantitatively, how many years will it be before the distance between these galaxies is 10% more? How many years will it be before the distance is twice what it was? And that answer to that question, how many years will it be before the distance grows by 10%, is the same for any two galaxies. In other words, because the distance to different galaxies is proportional to their velocity that we see, it doesn't matter which galaxy you pick, as long as you ask the question, how many years will it take for the distance to grow by a certain number, you will always get the same answer. So we can talk about the relative size of the universe. We can say the universe was half its current size. What that means is the distance between any two galaxies was then half of what it is today. That's a perfectly sensible concept. So, cosmologists invent something called the scale factor to the universe. The scale factor is a number which we set by convention equal to 1 today. And what the scale factor is telling us is the relative size of the universe. So when the scale factor was 1/2, that means that all the galaxies in the universe were half their current distance. When the scale factor is 2, everything will be twice as far apart as it is now. So one of the major projects that you want to complete, if you consider yourself to be a cosmologist, is to understand what the scale factor was doing as a function of time. So this plot shows the basic idea of what the scale factor does in an expanding universe. Right now it's getting bigger. Galaxies are growing apart from each other. We say that the universe is expanding. If you trace it backwards, it is, number one, very much smaller. We can trace it all the way back to 0. We don't necessarily think that we know what happens at 0, so we call it the Big Bang. The Big Bang, it's important to emphasize, is not a crucial part of our understanding of cosmology. It's a label we give to the place where we don't know what's going on. We know very well what's going on 1 second after the Big Bang, so we talk about the Big Bang as if we understand it, but really it's just a marker for our ignorance. Nevertheless, 14 billion years ago, there was something going on that we called the Big Bang, and we understand that everything there was squeezed on top of everything else, and it was expanding. So we believe, as we'll talk about very soon, that the rate of expansion in the past was bigger than the rate of expansion is now. So when we draw this plot, it has a sharper slope in the past than it does today. One of the things we would like to understand about this plot is its exact form from the Big Bang to today and into the future. One of the most surprising results of cosmology in the last 10 years is that today the expansion rate of the universe is going up. The universe is not only expanding, but it's accelerating, and that is why we believe in dark energy. So if we want to understand this phenomenon of the expansion of the universe in the context of general relativity, we remember that what Einstein tells us is that it's stuff in the universe that leads to the curvature of space-time. So the first question we should ask is, what kind of stuff is there in the universe? And even before we answer that question, we need to know what kind of stuff could there possibly be? What are the different forms of matter or stuff that could possibly fill the universe before we actually even go out and look at the universe and ask what we actually see? So let's first think about the things with which we are most familiar: the Earth, the Sun, or the galaxy. These are collections of particles. The Earth is made of particles. We talked earlier about atoms. The Earth is made of atoms. The Sun is made of individual atomic nuclei and electrons moving around, but they're made of particles. And these particles are bound together. So the Earth is bound together under the gravitational field of all the stuff in the Earth, likewise for the Sun, likewise for the galaxy. The Milky Way galaxy is bound together by the mutual gravitational force of all the 100 billion stars in it. So the first crucial thing about the expansion of the universe is that bound systems do not expand. So if you have two galaxies in the universe, each galaxy is orbiting under its mutual gravitational force. The distance between those two galaxies is getting bigger, but the galaxy itself is not getting bigger. The Earth is not getting bigger, you are not getting bigger, or if you are getting bigger, it is not because of the expansion of the universe, it's because of those donuts. So the bound systems do not get stretched along with the universe. And this is sort of a subtle thing that people are initially reluctant to believe, but it really is true. And in fact, it's the only way that you could even make sense of the claim that the universe was expanding. If everything in the universe, including people and atoms, expanded along with space, that would be exactly the same as nothing expanding. We only measure the distances between two objects in terms of the size of something else. If the size of everything increases, your rulers get stretched, the number of meters in between you and some distant galaxy wouldn't be seen to change. When we say that space is expanding, what we mean is the number of atoms that it would take to stretch from you to a distant galaxy is getting bigger. That's because the atoms are fixed and the galaxies are moving away. Absolutely strictly speaking, there's an equally good way of thinking about this in which the distance between galaxies is constant and all of the atoms are shrinking. That's just a really silly way of thinking about it, so we don't do that. It's much more convenient to think of atoms and you and me and the sun and the galaxy as remaining fixed in size, and the space in between the galaxies is getting bigger. But while the universe is expanding, even though atoms or particles do not stretch along with it, they become more dilute. More and more space is coming into existence. So if we draw a really big box, one that contains many, many hundreds of galaxies, and we say, how many galaxies per volume of space are there, that number will be going down. Space is expanding. The number of galaxies is basically not changing. The number of atoms is certainly not changing. So the number of atoms per cubic megaparsec, or the number of atoms per cubic centimeter, is going down. So we say that things are diluting away as the universe expands. Now, matter, to a cosmologist, is any set of particles that are moving slowly compared to the speed of light. Matter are things that get their energy from their mass. So Einstein, among his other accomplishments, said E equals mc squared. The interpretation of that equation, E equals mc squared, is not really energy equals mass times the speed of light squared. You need to attach some extra words to that equation to make sense of it. E equals mc squared is telling us that the rest energy of an object, the energy it has when it's not moving, is its mass times the speed of light squared. That's the minimum amount of energy that something can possibly have, and it's a constant. The mass is not changing, the speed of light is not changing. So the reason I'm going through this is to emphasize that the energy per particle is not changing if the particle is moving slowly compared to the speed of light. That, to a cosmologist, is what we call matter. As opposed to matter, we have radiation. We could have photons or other particles that are moving at the speed of light. If you're moving at the speed of light, your mass is zero. Your energy is not coming from E equals mc squared if you're moving at the speed of light. It comes from the frequency at which you're vibrating. But that frequency is changing as the universe expands because of this redshift. The cosmological redshift takes short wavelength, high energy photons and stretches them into long wavelength, low energy photons. So for particles that are moving slowly, E equals mc squared, and E is a constant. The mass per particle is a constant, so the energy per particle is a constant. But for particles moving at the speed of light, the energy per particle decreases as the universe expands. Photons and other particles that cosmologists call radiation lose energy as they become older and older in the history of the universe. So that's the important difference to a cosmologist between matter and radiation, how the energy density changes. The number density of particles is just how many particles per cubic centimeter. So the energy density is how much energy per cubic centimeter. In a region that grows along with the universe, the number density is constant. You're not creating new particles. But in a fixed centimeter, a cubic centimeter of space, the energy density will go down. The number density will go down, particles become more dilute, and therefore the energy density goes down. But the important difference between matter and radiation is that the energy density in radiation goes down more quickly. In radiation, not only do the particles dilute away, becoming less and less per cubic centimeter, but every particle loses energy. So this picture shows us basically what is happening as the universe is expanding. This is not a fixed amount of space. I've drawn a box that is getting bigger as the universe expands. So the number of particles in the box is a constant. The number of photons in the box is a constant. But the density per cubic centimeter of both particles and photons is going down, the energy per cubic centimeter is going down, but the energy in photons, in radiation, is going down more quickly because every photon is losing energy. So why belabor this point? The point is that the total energy in all the universe, in radiation, goes down more quickly than the total energy in matter. So you expect that as the universe gets older and older, matter will eventually win. There will eventually be more energy density in matter than in radiation, because the radiation has an energy that is going away more quickly. Contrary-wise, in the past, the energy density of matter is less important than the energy density of radiation. In the past, when all the photons were squeezed together with shorter wavelengths and higher energies, it was the photons that were winning. The photons were dominating. So a cosmologist will say that in the past, the universe was radiation dominated. It was the radiation that was important for the expansion of the universe. After that, it became matter dominated. So if you didn't know anything about the universe, if you didn't look out at the universe and discover the dark energy, if you pretended you were a cosmologist or an astronomer from 20 years ago, you would say that the things that could possibly be in the universe are either matter or radiation. It seems like those are the only possibilities: particles that are moving slowly compared to the speed of light, and particles that are moving fast compared to the speed of light, that is to say, at the speed of light or only slightly less. Then what we want to do is put that idea to work. Understand in the context of general relativity how matter and radiation create the curvature of space-time. So in general, if you weren't in a simple context like the expanding universe, the concept of the curvature of space-time can be arbitrarily complicated. Space can be curved in all sorts of different ways. Just imagine a simple two-dimensional sheet of paper. Imagine all the different ways you can crumple it and bend it and twist it. A four-dimensional space-time can be crumpled and bent and twisted in correspondingly many more ways. So space-time curvature can be very complicated. But luckily for us, the universe is a simple place. So for the next couple lectures, what we're going to be doing is ignoring the fact that there are lumps in the universe. Well, for this lecture anyway, we'll be ignoring that there are lumps. We'll be approximating the universe as perfectly smooth, imagining that all over the place you have exactly the same density of stuff. Then, in that very nice circumstance, the curvature of space-time becomes very simple. There are only two different forms which the curvature of space-time can take. One is the expansion of space itself. The very fact that space is getting bigger adds a component to the curvature of space-time. One way in which space-time can be curved is that space gets bigger as a function of time. That's one way. The other way is that even without expansion, space can be curved all by itself. So forgetting about the fact that the universe is getting bigger, just looking at the universe at one instant of time, you have a three-dimensional space, and you can say, is that three-dimensional space flat or is it curved? What kind of curvature does it have? And there are different possibilities. So let's start with that possibility. Let's start with the curvature of space before adding in the expansion of the universe. So now we get to forget about time. We get to think about three-dimensional space and ask, is it flat or is it curved? So what does that mean? A flat geometry to space means that Euclid was right. Our good old high school geometry that you get by drawing things on this tabletop, which is perfectly flat, has certain rules. For example, if you draw a triangle in space, you add up the angles, the three angles inside the triangle, there's a rule that says you will get 180 degrees every time. That is actually not a hard and fast law of nature. That is a feature of a particular kind of geometry, which we call flat. It turns out to be true on this tabletop, but if you're a geometer, if you're professional, you imagine other possibilities. For a long time, people tried to prove that it needed to be the case, that the angles inside a triangle would have to add up to 180. Eventually they gave up because they realized it wasn't true that it had to add up to 180. There were other possibilities. So we can imagine that space itself is curved. The good news is that space is the same everywhere. So the curvature of space is just a number. It's a number that changes as a function of time, but right now we're looking at the universe at one moment in time, and we say space is either positively curved, negatively curved, or zero curvature, that is to say flat. There's only three possibilities. So this picture shows you those three possibilities. These three possibilities are demonstrating the operational difference between space being flat, positively curved, and negatively curved. If you're in a positively curved space, you draw a big triangle. It's like drawing a triangle on the surface of a sphere. And you can do that. You can do that at home. You can add up those angles inside. Every triangle you draw on the surface of a sphere will have the property that the angles inside add up to greater than 180 degrees. The precise number of degrees they add up to will depend on the size of the triangle you draw. In a limit, when you go to a very tiny triangle, you'll come close to 180. As the triangles become bigger and bigger, it'll get bigger and bigger angles inside. So you could do that. You could do that to the universe and ask what its curvature was. You could even get that the angles inside added up to a number less than 180 degrees. In that case, we would call it negative curvature. And instead of living on the surface of a sphere, it would be like living on the surface of a saddle, something that bent in different directions in different regions. So this is something that we can go out there and test. The first person to actually think about these possibilities in a systematic way was Carl Gauss, a 19th century mathematician, and in fact he went out there and tested it. He drew a big triangle in the mountains near Hanover, and he measured the angles inside. He got 180 degrees up to his experimental error. It's an interesting thought experiment to ask if he had better precision instruments, would he have invented general relativity? Probably not is the answer, but he was a smart cookie, so you never know. So that is the possible scenarios for the curvature of space. Space could be flat. Euclid could be right. Space could be positively curved, like the surface of a sphere, or space could be negatively curved, like the surface of a saddle. The curvature of space is one of the two contributions to the curvature of space-time in a smooth expanding universe. The other contribution is just the expansion of the universe. So Einstein says that the curvature of space-time is being driven by the stuff that is in the universe. In other words, there should be some equation that relates the stuff that is in the universe to the curvature of space-time, in other words, the curvature of space and the expansion rate of space. So that equation was in fact derived from Einstein's equation by Alexander Friedmann, who was a Russian cosmologist. He derived this equation, which is the most important equation in cosmology, in 1922. Remember that relativity was only invented, general relativity, in 1915, and there was something else going on at the time called World War I, when general relativity was put together. But soon thereafter, Friedmann, who served in World War I, looked at what general relativity had to say about the expansion of the universe, and he came up with an equation. Sadly, he died in 1925 of typhoid, and it wasn't until 1929 that Edwin Hubble found that the universe is in fact expanding. So here is Friedmann's equation, the most important equation in cosmology. It's what tells us how the expansion of the universe responds to the stuff inside the universe. On the left-hand side, you have again some constants, some numbers, 8, pi, g, and 3. G is Newton's constant of gravity, familiar from Isaac Newton. Rho, is the Greek letter rho, is the energy density, the amount of energy in every cubic centimeter of space. It's going to change as the universe expands, but in this approximation where everything is very smooth, it's the same number from place to place all over the universe. So rho, the number of ergs per cubic centimeter, the amount of energy in every little part of the universe, is what drives the curvature of space and time in this way of thinking about things. So, on the right-hand side of the equation, you get two contributions to the curvature of space-time. The first contribution comes from the expansion. The second one comes from the curvature of space. So the expansion of the universe, remember, is measured by the Hubble parameter. Hubble was the one who told us that the number h is the constant of proportionality between the velocity of a distant galaxy and the distance to it. So the bigger h is, the faster the universe is expanding. So the particular way that h enters the curvature of space-time is in the form h squared. I don't have any simple, fun explanation for why it's h squared rather than h cubed. It turns out to be the Hubble parameter squared that is a feature of the curvature of space-time. And to that we have added k, the curvature of space itself. So the Friedmann equation is telling us that if you know the energy density, the number of ergs per cubic centimeter in the universe, and you know the Hubble constant, the rate at which the universe is expanding, then you can predict the curvature of space. Or you could do it in any other combination. If you knew the energy density and the curvature of space, you could predict the Hubble constant. Or best of all, if you could separately measure the Hubble constant and the curvature of space, then you would know what the energy density is going to have to be. This is going to be a crucial ingredient when later on we're going to say that dark matter and dark energy are really 95% of everything that there is. You can say that if ordinary matter is 5% of the universe, and by looking at gravitational fields we find new stuff, we find dark matter, 25%, dark energy, 70%, how do you know there's not something else that is even more, much, much more than there is dark matter and dark energy? This equation provides the answer to that. If you can separately measure the Hubble constant and the curvature of space, you know the total energy density of the universe. You're not leaving anything out. This is a manifestation of the usefulness of general relativity. Everything gives rise to a gravitational field. Everything makes space-time curved. So if you can measure the curvature of space and time, you've found everything. So what we're going to be claiming later on in the lectures is that we have measured the Hubble constant and we have measured the curvature of space, so we do know the energy density. We know how much stuff there is in the universe. And when we add up ordinary matter, and dark energy, we reach that number. There is no room for any more stuff in the universe that we haven't yet found. There could be 1% more here or there. There could be trace things that we don't know, but most of the universe we claim we understand what it is. So that's an important accomplishment. More specifically, what you like to do as a working cosmologist, it's nice to think that you have everything. What you want to do is to take this equation, you want to solve it. So remember, what we want to do is to plot out the scale factor as a function of time. In other words, what was the size of the universe at different epochs in cosmological history? So this is the equation that tells us that. If we not only know the value of rho, the value of the energy density, how many ergs are there in every cubic centimeter of space, not only do we know the value of the Hubble parameter and the value of the curvature of space, but if we know how the energy density changes as the universe expands, then we can solve this equation uniquely for the scale factor throughout the history of the universe. I can tell you, if you give me what the energy density is and how it changes, a unique history for how close together things were in the universe as a function of time. So at different points later on in the lectures, we'll be saying things like, when the universe was 1/1000th its current size, which is 400,000 years after the Big Bang. How do I know when the universe was a certain size, what time it was in the age of the universe? This is how I know. I plug into this equation and it tells me how big the universe is as a function of how old the universe is, which is the crucial question for cosmology. So this is the game that we're going to play for the rest of these sets of lectures. We're going to determine what is in the universe. What is the universe made of? Ordinary matter, and dark energy will be the answers. Remember, in the past, the universe was radiation dominated. Radiation today is very unimportant, so we even have to keep careful track of the radiation in today's universe because it used to be important in the past. Then we will use this equation, the Friedmann equation, to extrapolate from our current conditions back to the earliest times in the history of the universe. With that extrapolation, we will make predictions. And then we will test these predictions against stuff we observe today. It is never the case in this whole procedure that we say things like, well, it was Einstein who came up with this equation, it must be right. We're always trying to test these ideas. So we have an equation, it seems to work pretty well. How well do we test it? How well do we have empirical data that says this equation must be right? So as we will see in a few lectures, we can trace this equation, the Friedmann equation, back to when the universe was only a few seconds old after the Big Bang. We can use that extrapolation to make predictions about what the universe looks like right now. Those predictions will turn out to be true. This equation, the Friedmann equation, and Einstein's equation on which it is based, are, at least to a very, very good approximation, telling us something true about how the universe behaves. In lectures to come, we'll put that truth to use to see how the universe has evolved.